In 1956, mathematics professor John McCarthy sent out a proposal for a summer workshop at Dartmouth College. His goal was to establish a brand new academic discipline, which he officially named artificial intelligence. McCarthy wanted to gather top researchers to test a specific hypothesis that every aspect of human learning could be so precisely described that a machine could successfully simulate it. 6 years prior, Alan Turing had already asked the question, can machines think? Yet at that time, artificial intelligence was strictly theoretical. It consisted almost entirely of complex logic and mathematics written out on paper. While this paper brain was brilliant, mid-century hardware completely lacked the physical power to process real-world data. These massive, room-sized machines relied on crude mechanical switches and vacuum tubes that could barely handle simple calculations. For 7 decades, computer engineering focused on building the physical muscle necessary to support the advanced theoretical brain McCarthy and Turing originally designed. Today, our entire computing infrastructure relies on silicon-based microchips mounted to standard green circuit boards. Silicon comes with strict physical limitations. As data moves through standard copper traces, it encounters electrical friction, generating high levels of noise and severe heat. This forces the hardware to throttle its processing speed to avoid melting down. To manage these hardware flaws, manufacturers stack bloated software layers on top of the silicon. These layers act as an intermediary operating system, requiring constant driver updates to translate commands between the user and the struggling metal below. Modern operating systems are also built with heavy telemetry. Telemetry is an automated process where your machine continuously harvests personal data and sends it back to corporate servers while enforcing planned obsolescence. Running a complex neural processor on this high-friction data harvesting architecture creates a severe bottleneck. The processing power is drained by the software layers before it can ever execute tasks at real-world speed. Discarding the high-resistance environment of silicon entirely allows local AI to operate with the velocity required for home use. This is 8XOS, an infrastructure operating system that moves beyond the desktop and mobile labels of the past. 8XOS functions as a bare metal operating logic, engineered from the ground up to execute tasks within a non-silicon environment. The physical foundation relies on carbon polyamide and ceramic platforms. It integrates its logic directly into 24-karat gold, legacy copper, and 90% pure silver diodes. This architecture creates what is known as a metallic bus. By utilizing these precious metal alloys, data flows with virtually zero electrical friction compared to the jagged, noisy pathways of standard silicon chips. By migrating computing logic away from bloated software layers and embedding it physically onto highly conductive precious metals, the hardware achieves velocity that silicon cannot match. In traditional computing, heat is the ultimate enemy of speed, causing hardware to degrade and artificially limit its own performance. Instead of relying on a standard digital crystal clock to keep time and regulate processes, 8XOS uses a protocol called thermal sync. In this system, execution speed is dictated by the thermal gradient flowing across the 24-karat gold parent board and the copper penny array. The heat itself provides the rhythmic heartbeat of the processor. This is controlled by the TMPTEG, or Thermal Management Processor. It enables a regenerative compute cycle, capturing waste heat radiating off the metals and converting it back into usable processing power. Because of this extreme thermal efficiency, the entire operating system runs natively on an ultra-low 3.0-volt power standard. By integrating logic into self-powering metal, 8XOS achieves a hardware direct state. It communicates with monitors, mice, and peripherals natively through raw electrical pulses, requiring exactly zero-signed software drivers to function. This precious metal architecture allows users to host an agile node, a modular, decentralized data center right inside their own home. Unlike a traditional PC that degrades over 4 years, the non-oxidizing gold and copper 8XOS node remains stable for decades, achieving material immortality. Operating on the sovereignty protocol, this air-gapped node cannot sync local data to external corporate servers. This zero-strings logic moves control back to the individual, replacing the industry standard of leased software with true ownership of the underlying metal. This is the mechanism of digital self-defense. It took 70 years to travel from the purely theoretical mathematics sketched by pioneers in the 1950s to the physical reality of an AI node sitting directly on your desk today. The modern digital world is built on strings of extraction and control. 8XOS is the knife that cuts them. By merging the theoretical brain of artificial intelligence with the raw muscle of precious metals, 8XOS turns your hardware into a completely sovereign fortress.